Hello London, Servus München. Great to be back here. Well, everything you've seen today and what's upcoming runs on something. That something is data, energy, and compute. In particular, the investments we're seeing into computing, into the AI infrastructure, are kind of mind-blowing, right? I pretty much have to update this slide every day because there's a few more billions poured into by another hyperscaler into all the AI infrastructure, right? So the CapEx is very high. But it's not just an economical cost, there's also, of course, an environmental cost attached to this, right? Especially if we're looking into AI training, AI inference of some of these data centers that run on natural gas, it's kind of ridiculous how much CO2 is emitted, right? And that is surely not sustainable forever. Therefore, the optimization, the objective function of this AI infrastructure era is tokens per watt or tokens per euro. And we can optimize that on the software side with more efficient models, but also on the hardware side with more efficient compute, with more efficient chips. And of course, all the chip manufacturers are investing in this. Just last week, TSMC said the number one constraint for chip design these days is energy efficiency and not raw compute power anymore, right? And it's not just the chip manufacturers. Every hyperscaler out there is investing into their own FPGA-based custom silicon, namely language processing unit, tensor processing unit, neural processing unit, all of these fun things. And of course, at Reply, we're also part of this. And here you can see an example from us, which is a real-time computer vision application that helps an operator to assemble certain parts. And all of this runs on an edge device, pretty much the size of this remote is the board. And the chip, it runs a neural processing unit with that custom model. It's probably the size of such a button, right? And all of that custom model runs completely locally on the device with real-time computer vision, fully local, fully sovereign. And that's actually also part of our IPJ commitment, which is an EU flagship program for the sovereign cloud edge continuum. Besides the new GPUs and besides new FPGA-based accelerator chips, also complete new computing paradigms are emerging, namely neuromorphic, quantum, and biological computing. And for this, I ask Johannes to tell us a bit more about it.
Thanks a lot, Rene. Let me point out that these new modalities of compute are not just variations on established silicon. They're really radically new ways of doing computations. Let's start with neuromorphic. Can neuromorphic help us to overcome the energy hunger of AI? Neuromorphic chips work a bit like the brain. They use spiking neural networks, which is event-driven, sparse computation. In a traditional network, you have to power every neuron with every cycle. In a spiking neural network, a node only fires once inputs cross a specified threshold. This is really frontier technology, so we are partnering with SpinCloud, which is a university spin-off based in Germany and the UK. This is European technology, which has sovereignty included and built in. Now to the energy. Our experiments show a decrease of roughly 75% in energy consumption while achieving a similar accuracy. Now, for a computer vision task, you could pair this with other innovative technologies like event cameras. Those are cameras which, similar to the human eye, only record what is new in each frame rather than everything, the full frame at every time, leading to even more efficiency.
And let me just repeat, like 75% energy reduction for similar accuracy for the same task, right? And I think such technology might be actually the only way how we can stay competitive in the AI race in Europe with our high energy prices, right? We need to be more efficient there. And 75% reduction is no joke, especially with a sovereign technology, right? So I'm super excited about this collaboration. But what about quantum, actually?
Yeah. So also in quantum, there's a lot of activity in Europe to create sovereign quantum technologies. However, we have to state that in terms of investment, the US is leading the way big time. So there's something to catch up. Now, quantum properties belong to the small things, to atoms, to molecules, and they don't really want to survive at macroscopic big scales. That's why our everyday world is not quantum mechanics and why it's difficult to grasp. This is also why building a fault-tolerant quantum computer is really a daunting task, but progress is steady. Here's something which should make you sit up. Google has just announced or set 2029 as its deadline to be quantum safe. This is 6 years earlier than the estimates done by NIST, which was originally 2035. The latest research shows that breaking an RSA 2048 algorithm would now only require about 1 million noisy qubits, which is down from 20 million as estimated earlier. So this means the runway is much, much shorter than we anticipated and than we planned for.
And you said 2029, right? So that's 3 years from now. That's pretty much nothing, because we don't have 3 years to wait, because there are certain actors out there that exercise a thing called harvest now and decrypt later. What that means is they're storing all the encrypted traffic today, and once they have a powerful enough quantum computer, they will just crack open the box, and they're probably not going to tell us when that happens, right? So make sure what you share online, even if it's encrypted, right? It might not be that safe for the future anymore. And the shocking part is that only 5% of enterprise companies have deployed post-quantum cryptography today, right? And so the time to act is now, I guess.
I agree, it's really urgent to act. On the flip side, though, this means that we'll also reap the benefits of quantum computing earlier than anticipated. So Reply is currently leading a research project within the Munich Quantum Valley, together with partners such as Fraunhofer BMW, in which we deliver a benchmarking framework that tests where quantum algorithms can really beat classical solutions from a practical use case-driven point of view. If you're interested in optimization problems, chemistry simulations, machine learning applications, please, I invite you to join our dedicated session in the afternoon. Efficient and accelerated computing are a path to general artificial intelligence. But how much closer to real intelligence could you get by using a real brain? At Reply, we are a front runner in the field of biological computing. Together with our partner Cortical Labs and the academic partners at Milano, Padua, and Genoa, we are experimenting with a system that combines human neurons with silicon chips. On the one hand, this system has a classical interface like a computer, but the back end is an incubator with living biological tissue that actually performs the computations. In order to stay alive, that needs gases like CO2, nitrogen, oxygen, and the human neuronal cells are sitting on a multi-electrode array chip, which is like a chessboard layout where the neurons are either stimulated with controlled pulses by the electrodes, or the neuronal electric activity is read out. Now, one of the first applications we are doing with these systems are simple tasks like playing a game or doing control systems. An example, which you see here on the screen, is the game of Tong, where a paddle has to be moved up and down to intercept a moving ball. You see here a picture of the system and how the paddle is moving. While the neuron activity is recorded, you can see the neuronal spikes. And you can also see to the right of the game that the chip has dedicated regions to either control the movement of the paddle or to record the input of the screen. The learning paradigm here reflects what is called the free energy principle. Biological systems stay in balance by avoiding chaos. They reduce uncertainty while at the same time minimizing their energy. So the system learns to prefer behaviors which has predictable outcomes. So what can we do with this? We are also venturing into medical translational applications. Glioblastoma is a very, very aggressive brain tumor for which a truly effective treatment doesn't really exist today. We study with this system how electrical signals applied to neural tissue can attract tumor cells to controlled zones. The idea is concentrate the tumor in one region from which it can be safely removed much more effectively, reducing the risk of silent migration. This is really a fascinating new system, and I'm happy to tell you that you can have a look at the system in the upstairs demo area here in Munich. The last example shows clearly what I think is true for all these new modalities of compute. There's an obligation to innovate so we can ensure and shape the future to the greatest benefit of humanity. Thank you.